Hello dear students, welcome to Gate Wallah. So I hope you are doing well. And in this session we will discuss about the external force convection. So this is a one short series, and whatever the concept involved in the uh, external force convection, we will cover all those concepts in a one shot. Okay, now what topics we will cover in this session? So first we will cover the basics of convection, like convection heat transfer is governed by the Newton's law of cooling. Then there are three types of convection heat transfer: free convection, forced convection, and the mixed convection. So some basic things, right? So first we will cover the basics of convection heat transfer. Then after that we will cover the dimensionless numbers which are used in the convection heat transfer, like Nusselt number is there, and Prandtl number is there, Reynolds number is there, right? And Grashof number is there. So there are some dimensionless number which are used in the convection heat transfer. So we will discuss about those dimensionless numbers. Then after that we will discuss about the hydrodynamic boundary layer concept, right? Hydrodynamic boundary layer thickness and the turbulent boundary layer thickness, and after that we will discuss about the relation between these two, right? And after that we will discuss some some empirical expression, sorry. After that we will discuss some empirical relations which are used to calculate the Nusselt number, okay? So let's start our discussion. So if I'm talking about the convection heat transfer, so this convection word is made of two terms, right? This convection word made of two terms or two words. That first one is conduction and the second one is the advection, right? So convection heat transfer is made of two terms: conduction plus advection, right? And we already discussed about the conduction heat transfer, right? So here we are not discussing too much about the conduction, but convection is made of two terms: conduction plus advection. If there is no conduction, there is no convection, right? If there is no conduction, there is no convection. Without conduction, you can't say there is a convection, right? Conduction is required for the convection heat transfer. So conduction plus advection both is required for the convection heat transfer, right? If conduction is zero, so that is not convection. That is not convection. That is not heat transfer. That is only advection. So question is that what is the advection? So advection means fluid motion. Right? If there is no advection, then there is only conduction. So again, if there is no advection, no convection. That is conduction then. Is it fine? So advection means fluid motion. Now this fluid motion is created, or this fluid motion is induced in two ways, right? One is freely, or you can say naturally. Right? So if fluid motion is created freely, then that type of convection is known as free convection. But if the fluid motion is created with the help of some external agent, if the fluid motion is created with the help of some external agent or forcefully, then that is known as the forced convection. Then that is known as the forced convection. Right? And there is a mixed convection also. And this mixed convection is combination of free convection and the forced convection. So mixed convection is combination of free convection and the forced convection. forced convection, combination of free convection and the forced convection. Is it fine? Now see, whatever the type of convection heat transfer is there, whatever the type, either it is a free or force or mix, that convection heat transfer is governed by the Newton's law of cooling. That convection heat transfer is governed by the Newton's law of cooling. So that is very, very important thing, that convection heat transfer is governed by Newton's law of cooling, is governed by Newton's law of cooling. And we know that what is the Newton's law of cooling? And we know that what is the Newton's law of cooling? If there is a plate, and plate temperature, if there is a plate and the plate temperature is Ts, if there is a plate and plate temperature is Ts and fluid temperature is T infinitive, and I am assuming that Ts is greater than T infinitive. So what is the convection heat transfer from this plate? So I can say that convection heat transfer is equal to, that is HA, and this is Ts minus T infinitive. We already discussed about this Newton's law of cooling earlier, right? So what is the H? That H is convective heat transfer coefficient. H is convective heat transfer coefficient, or you can say average convective heat transfer coefficient here. Average. Okay, so let's later we will discuss about the average and the local. So it is simply convective heat transfer coefficient. A is the area. A is the area for convection heat transfer. A is the area responsible for convection heat transfer. What is T? Ts is surface temperature. And what is T infinitive? This T infinitive is fluid temperature. Right? And what is the unit of H? That unit of H, simply you can say that unit of H, that is watt per meter square Kelvin. Watt per meter square Kelvin, or watt per meter square degree Celsius. We already discussed about these units, no? Right? And in terms of the fundamental dimensions, so that is Newton watt. Watt is joule per second. So Newton meter per second, and that is meter square, and that is theta. Okay, so meter, and ultimately this is Newton, and this is mLT minus 2 divided by second. So this is T. Meter, this is L, and this is theta. So L cancel out. So this is m T minus 3 and theta minus 1. M T minus 3 theta minus 1. So what is the unit of H? That unit of H is m T minus 3 theta minus 1. So this is the unit of, this is the fundamental dimension for the H. M T minus 3 theta minus 1. And H is a convective heat transfer coefficient, which depends on the number of parameters, which depends on the number of things, right? H depends on number of parameters. Right? Like first, right? Free convection or forced convection. Convection is free convection or forced convection. Convection is free convection or forced convection, because for free convection H value is different. For forced convection, that H value is different, right? So that value of H depends on the free convection or forced convection, right? Second, that value of H depends on the type of the fluid. That means fluid is liquid or gas. Next, this convective heat transfer coefficient depends on type of fluid motion, type of fluid flow, I can say type of fluid flow. That means flow is, that means flow is laminar or turbulent. Flow is laminar or turbulent, right? Next, it depends on the surface roughness. It depends on the surface roughness. That means, right, that surface roughness, that is mirror polished or rough. So H value depends on the that also, surface roughness. Next, orientation. Next, orientation of the surface. Orientation of the surface. Orientation of the surface, that means surface is horizontal or surface is vertical or surface is inclined. So H value depends on the number of things. It is not like a thermal conductivity, right? H is not like a thermal conductivity. That thermal conductivity only depends on the type of the material, but here that H value depends on the number of parameters. Is it okay? Right? Now, next, let's start our discussion on free convection and the forced convection. Actually, see, in the free convection, in free convection there is no external agent. In free convection there is no external agent, but in case of the forced convection, that external agent is required, right? So you might be thinking, ki, sir, then in free convection, how the advection occurs, how the advection takes place. Okay, so to understand this, now let's see free convection. Free convection. So to understand the concept of the free convection, I am considering a plate here. This is the plate. This is the plate. Right, this is the plate. To understand the free convection, I am considering a plate, and let us assume this plate temperature. This plate temperature is Ts. This plate temperature is Ts. Right, and above this plate, there is a, above this plate, I am assuming there is a fluid. So that fluid is not in motion, na? There is no any external agent is there. There is no any external agent is there. Okay. Okay. So this fluid temperature is T infinitive. This fluid temperature is T infinitive. And again I am assuming here, this Ts is greater than the T infinitive. Ts is greater than T infinitive. Now see here, if Ts is greater than T infinitive, and if you are observing the fluid particle which are present near to the surface. Near to the surface means, see, if you see this coordinate system, this is the x-axis and this is the y-axis. Right, near to the plate, that means at y is equal to 0. I am talking about at y is equal to 0. So at y is equal to 0, that fluid particles and the plate particles are in direct physical contact. In direct physical contact, see, if you see here, if I am assuming this is the fluid particle, see here, this is the fluid particle. This is the fluid particle. Fluid particle has temperature that is a T infinitive, and there is a plate particle, and this plate particle has a temperature that is Ts, and Ts is greater than T infinitive. I am assuming here Ts is greater than T infinitive, and if Ts is greater than T infinitive, then that heat transfer occurs from the plate particle to the fluid particle. So if I ask you that one question, what is the mode of heat transfer? If I ask you one question, what is the mode of heat transfer at y is equal to 0? So you see here that fluid particle and the plate particle are in direct physical contact. If plate particle and the fluid particle are in direct physical contact, then that mode of heat transfer is conduction. That mode of heat transfer is conduction. So at y is equal to 0, what is the mode of heat transfer? That mode of heat transfer is conduction. Is it fine? Now see, if you are observing the particles which are present at y is equal to 0, that take the heat energy from the plate, via conduction. Okay, so if I considering these two particles, these fluid particles which are present at y is equal to 0, take the heat energy from the plate via conduction. Okay, now see, if you are observing these two particles extracting the heat energy from the plate, or heat energy is flowing from the plate to the fluid. So these fluid particles are heated, and we know that as temperature increases, the density decreases. As a temperature increases, density decreases. If density decreases, then the fluid particle become lighter. If the fluid particle become lighter, so this fluid particle start to moving upward. These fluid particles are start to moving upward. Right. So the place of these fluid particles are vacant. That space of the fluid particles are vacant. So these heavy particles, which are present away from the plate, so let us assuming two particles here, these particles which are away from the plate, right, and these particles having higher temperature, these particles having lower temperature, as compared to the temperature here now. These two particles having lower temperature. So if the temperature is low, that means density is high. If density is high, that means these particles are heavier as compared to these particles. So these particles are moving up and these particles are moving down. Again I am repeating now, right? These two particles are taking the heat energy from the plate, right? If taking the heat energy from the plate, temperature increases. If temperature increases, density decreases. If density decreases, the fluid particles becomes lighter. The fluid particles are moving upward, and the particles which are present away from the plate having lower temperature or having lesser temperature as compared to this fluid particle. Is it fine? Now these particles having low temperature, so density is high. If density is high, that means these particles are heavier. If these particles are heavier, then whatever the space is vacated because of the moving of these particles, right, these space are filled by these particles. Okay, so that lighter particles moving upward and the heavier particles moving downward, right? This creates a current, convection current, and this convection current is nothing but the fluid motion only, right? So in case of the free convection, there is no external agent, but the fluid motion is created naturally. The fluid motion is created naturally. See here, this is the natural phenomena. That lighter particles moving upward and the heavier particles moving downward. This is the natural phenomena. And that's why this convection is known as the free convection. So please try to understand the order. There is a temperature difference. Between the fluid particle and the plate. Because of this temperature difference, the density difference come into picture, and because of this density difference, a buoyant force are acting in the fluid particle, and because of this buoyant force, that lighter particles are moving upward. So buoyant force come into picture. So whenever the free convection is there, na, the buoyant force come into picture. Is it clear? Is it fine? Right. So in the free convection, there is no external agent. So whatever the fluid motion is there, the fluid motion is because of this temperature difference. Because of this temperature difference, density difference is there, and because of density difference, a band force come into picture. Lighter particles are moving upward, heavier particles are moving downward, and in this way, that advection occurs. Is it clear? So this is about the free convection. This is about the free convection. Okay. Now free convection is also governed by the Newton's law of cooling, as I already discussed. Now come to the forced convection. Now come to the forced convection. Forced convection. Now see here, in forced convection there is some external agent. That external agent is required for the fluid flow, right? So I am considering a plate. So this is the plate. This is the plate having width, let us assume that is B, and which is perpendicular to the board or perpendicular to the monitor. So this is a plate. This plate having temperature that is a Ts, that fluid temperature, fluid is in motion. So let's see, this fluid is in motion. The temperature is T infinitive, velocity is U infinitive, right? Now if you see the coordinate system, this is the x-axis along the plate, that is the x-axis, perpendicular to the plate, that is y-axis, right? And there is an external agent. See, there is some external agent. That external agent may be fan, that external agent may be blower, that external agent may be pump. Is it fine? But there is an external agent, and because of that external agent, that fluid has a velocity U infinitive. Is it fine? Now see here, if you are observing at y is equal to 0, again at y is equal to 0, right? See, please try to understand this logic. At y is equal to 0. So at y is equal to 0, what happened? And that is experimentally observed. At y is equal to 0, right? That velocity of the fluid, at y is equal to 0, the velocity of the fluid is same as velocity of the plate. This is a practical observation. What is the meaning of that? Whatever the velocity of the plate have, the same velocity of the fluid also have at y is equal to 0. So if, let us assume, if the plate is moving with a velocity of 5 meter per second, so fluid is also moving at a velocity of 5 meter per second at y is equal to 0. That means there is no relative velocity between the plate and the fluid particle at y is equal to 0. There is no relative velocity. And if there is no relative velocity, then there is no sleeping. The sleeping, very, very important phenomena. The sleeping occurs, sleeping happens when the relative velocity exists. If there is no relative velocity, there is no sleeping. Right. So at y is equal to 0, whatever the velocity of the plate have, same velocity of the fluid also have. That means we can say no relative velocity between plate and the fluid. No relative velocity between the plate and the fluid. And this condition, see, this condition is known as, because if there is no relative velocity, again I am telling you guys, if there is no relative velocity, there is no sleeping. And that's why this condition is known as the no sleep condition. No sleep condition. That means at y is equal to 0, that u is equal to up. Right? If the plate is stationary, if I am assuming this, this plate is stationary. If I am assuming that plate is stationary, that means up is 0, and I can say u is equal to 0. So at y is equal to 0, u is equal to 0. But whatever the condition is there, plate is stationary or plate is moving, we know that this fluid particle having the same velocity as the plate have, right? So at y is equal to 0, I'm assuming then, to understand this concept, I'm assuming the plate is stationary. So at y is equal to 0, if you see, again, the same logic, this is the plate particle, this is the fluid particle. So at y is equal to 0, right? At y is equal to 0, these two particles, one is a fluid particle, another one is a plate particle. These two particles are in direct physical contact. If these two particles are in direct physical contact, this particle having temperature Ts and this particle having temperature T infinity, and I'm already assuming this, right? If I'm already assuming this Ts is greater than the T infinitive. The Ts is greater than the T infinitive. So if Ts is greater than the T infinitive, then that heat transfer occurs from the plate to the fluid. So what is the mode of heat transfer here? The mode of heat transfer is conduction. The mode of heat transfer is conduction, right? And due to conduction, these fluid particles are taking the heat energy from the plate, right? Since there is some external agent is there, so this external agent pushes this layer. Now this layer is moving forward, right? There is some external agent now. Once these particles are taking the heat energy from the plate, then there is some external agent. This external agent pushes this layer so that next layer come into contact with the plate. And in this way, that convection heat transfer occurs. So again, there is a conduction plus advection, plus here the advection is due to some external agent, right? And what happened in the mixed convection? In the mixed convection, these particles are moving forward also. These particles are moving forward also, in the forward direction. At the same time, some particles are moving upward also, because of that density difference. So in the mixed convection, external agent is there. So because of that external agent, the fluid particles are moving forward. Some particles are moving upward also, right? So that some particles are moving upward, and the particles which are away from the plate are moving downward. So convection current is also there. So because of the free convection, such type of advection occurs, right? Such type of advection occurs, and because of external agent, the fluid layer moving forward. So that is a free convection. That is a mixed convection. So mixed convection is combination of free convection and the forced convection. Is it fine? Now see here. Now, so again I am telling you guys, whatever the convection is there, either it is a free or forced, that is governed by the Newton's law of cooling. Okay. Now, come to the next concept, and that is let's start our discussion on the different dimensionless numbers which are used in the convection heat transfer. So various dimensionless numbers used in convection heat transfer. So that first number is very, very important, that is Nusselt number. So that Nusselt number is denoted by NU. This is the Nusselt number. So what is the Nusselt number? That Nusselt number, it is ratio of conduction resistance. It is ratio of conduction resistance offered by the fluid. It is ratio of conduction resistance offered by the fluid to the convection resistance, to the convection resistance of the fluid. Convection resistance of the fluid, because we know that for the convection, conduction is required now. So the conduction resistance also come into picture, but conduction resistance of what? Fluid, right? So Nusselt number is equal to, now see here, the ratio of conduction resistance, so conduction resistance is RTH conduction, okay, that is delta by KF, sorry, that is delta by, this is delta by K, na? So this is delta by, this is KF into A, fine. Since we are talking about the conduction resistance of the fluid, that's why I'm using the convective heat transfer so that's why I'm using the thermal conductivity of the fluid, okay. Now see here, next is the convection resistance. And what is the convection resistance? That is 1 upon HA. So I'm replacing this delta by another term, and that term is LC. What is the LC? That LC is a characteristic length, LC. So this is the LC, or I say RTH conduction fluid. I hope you can understand this. And this is RTH convection. Okay. So that Nusselt number is equal to, this is LC by KFA, divided by 1 by HA. So 1 by A cancel out. So ultimately you are getting this HLC by KF. So this is the mathematical expression for the Nusselt number. Nusselt number you can define in another way also, right? Mathematical expression will be same. That is a HLC by KF. But Nusselt number you can define in another way also, and that Nusselt number is equal to, that is, just see here, there is a conduction now. So this is the rate of convection heat transfer, to rate of conduction heat transfer to rate of convection heat transfer to rate of conduction heat transfer. Just we know that the rate of if the temperature difference is same, that means at that case, if temperature difference is same, at that case we can say that rate of heat transfer is the reciprocal of the thermal resistance, right? So if thermal resistance Nusselt number, this is the RTH conduction fluid to RTH convection, right? And we know that the rate of heat transfer is the reciprocal of, if delta T is same, then the rate of heat transfer is the reciprocal of the resistance. So directly we can write in this way also, right? So Nusselt number you can define in this way, the rate of convection heat transfer to the fluid to rate of conduction heat transfer to the fluid, right? Or you can define in this way, the Nusselt number is a ratio of thermal resistance which is offered by the fluid to the convection resistance, right? So this is the first dimensionless number, which is used in the convection heat transfer. The second dimensionless number you already know, I think, that is a Reynolds number. Reynolds number. It is denoted by RE, right? What is a Reynolds number? So my dear, the Reynolds number is ratio of, it is a ratio of two forces. Reynolds number is a ratio of two forces. One force is the inertia force, whereas the other force is the viscous force, right? So this Reynolds number is ratio of two forces, inertia force to viscous force. 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 Okay. And what is the inertia force? Inertia force is noted by Fi, and the viscous force is noted by Fe. If you're solving this, then what you are getting? You are getting this rho u Lc by mu, right? Or you can say u Lc by, that is mu. What is mu? Dynamic viscosity. What is mu? Kinematic viscosity, right? So that Reynolds number, mathematically Reynolds number, either you can write in this way or you can write in this way, right? What is the Lc? Again, that Lc is a characteristic length. Lc is the characteristic length. And what is the Lc? This Lc depend, the calculation of Lc, that characteristic length, that Lc is characteristic Lc is characteristic length. Lc is characteristic length. And the calculation of Lc depends on flow is external flow or flow is internal flow. So if flow is external, right? If let us assume this is a plate, right? If this is a plate and this dimension is, let us assume this is the A, and this dimension is, let us assume this is the B, right? And if flow occurs along the A, along the length, if flow occurs along the A, then in this case Lc is equal to A. But if flow occurs along the B, then Lc is equal to B. In this case, that Lc is equal to B, right? So in case of the external flow, right, in the direction, or I can say in the case of the external flow, if flow occurs along the A, then characteristic length is A. If flow occurs along the B, then the characteristic length is B. Whereas in case of the internal flow, that means flow inside the closed conduit. That conduit may be pipe, the conduit may be duct, but flow through the closed conduit, that is the internal flow, right? So in case of the internal flow, this Lc is 4 into flow area, that means cross sectional area, divided by weighted perimeter. This is the Lc. And in case of the non-circular closed conduit, or in case of the non-circular conduit, this Lc is also known as dH. What is the dH? This dH is hydraulic dia. This dH is also called hydraulic dia. Is it fine? Is it clear? So this is the Reynolds number. And what is the significance of the Reynolds number? Actually, Reynolds number tell us flow is laminar or turbulent. Either flow is internal or external, right? So based on the Reynolds number, we can easily comment that flow is laminar flow or flow is turbulent flow, right? So if the value of Reynolds number, if you are calculating the Reynolds number, and if this value of Reynolds number is less than or equal to critical Reynolds number, then you say flow is laminar flow. Flow is laminar flow. And if the Reynolds number is greater than the critical Reynolds number, there is a flow transition also, no? There is a transition of flow in a certain range of the Reynolds number, in a certain range of the value of the Reynolds number, there is a transition also, but here right now I'm not talking about the transition so much. So I say if the Reynolds number is, if you are calculated the Reynolds number, and if the Reynolds number is less than or equal to the critical Reynolds number, then flow is laminar, and if the Reynolds number is greater than the critical Reynolds number, then the flow is turbulent. Then the flow is turbulent. Flow. Right. And in case of the internal flow, again, see here, if I'm talking about the external flow, if I'm talking about the external flow, and if I'm talking about the internal flow, in case of the internal flow, the critical Reynolds number is 2000. In some books, it is given 2300 also. That is also correct. That is also true. That is also right. But in some books, the critical Reynolds number is 2000. So 2000, 2300 both are correct. Right. Here I am taking critical Reynolds number as 2000 for the internal flow. Whereas in case of the external flow, the critical Reynolds number, if nothing is mentioned in the problem, then take 5 into 10 to the power 5. 5 into 10 to the power 5. So for the external flow, the critical Reynolds number is 5 into 10 to the power 5. Whereas in case of the internal flow, the critical Reynolds number is 2000. Okay, now see. So this is second dimensionless number. Now third dimensionless number is Prandtl number. Prandtl number. Third dimensionless number is Prandtl number. It is denoted by PR. So what is the Prandtl number? What is the Prandtl number? The Prandtl number is a ratio of momentum diffusivity to the thermal diffusivity. Right? This Prandtl number is a ratio of momentum diffusivity. It is a ratio of momentum diffusivity to thermal diffusivity. Momentum diffusivity to thermal diffusivity. Momentum diffusivity to thermal diffusivity. And momentum diffusivity is nothing but the kinematic viscosity. Right? The momentum diffusivity is nothing but the kinematic viscosity. Right? So momentum diffusivity is shown by the nu, and the thermal diffusivity is shown by the alpha. So this is the Prandtl number. Right? And Prandtl number you can write in another way also, because see, nu is equal to what? Nu is equal to, this is mu by rho, matlab dynamic viscosity to density. The nu is a kinematic viscosity, and it is a ratio of dynamic viscosity to density. And what is the alpha? That alpha is the thermal diffusivity, and you can say this is Kf by rho Cp. So ultimately that Prandtl number is, this is 1 by rho is cancelled out. So this is mu Cp by Kf. Right? So Prandtl number you can define in this way also, and Prandtl number you can define in this way also. Both are correct. Right? Prandtl number is nu by alpha, right? Or Prandtl number is equal to mu Cp by Kf. What is a mu? Dynamic viscosity. What is the Cp? Specific heat at constant pressure. If there is a incompressible substance, then there is a only specific heat, because in case of the incompressible substance, there is no concept of the specific heat at constant pressure, specific heat at the constant volume. There is no concept in case of the incompressible substance. There is only specific heat. Right? And what is the Kf? The Kf is thermal conductivity of the fluid. Right? Cp is the specific heat at the constant pressure. If there is a compressible substance, then might be you're thinking about the Cp and Cv. So take the Cp here. Right? If simply I write that mu Cp by Kf, then in case of the compressible substance, because Cp and Cv is different. right? So might be you are confusing at that time. So simply I can write here mu Cp by Kf. Okay, so Prandtl number is mu Cp by Kf. Okay, now from it is from in this mathematical expression it is very much clear this Prandtl number is a function of the fluid properties, right? It depends on the fluid properties, right? Prandtl number, it depends on the Prandtl number depends on the fluid properties. Prandtl number depends on the fluid properties. Is it fine? Now what is the significance of the Prandtl number? Actually the Prandtl number tell us what is the significance of the Prandtl number. The Prandtl number tell us, see, in the case of the convection heat transfer, especially in case of the convection heat transfer, there is a concept of the thermal boundary layer and there is a concept of the hydrodynamic boundary layer, right? There is a concept of the thermal boundary layer and there is a concept of the hydrodynamic boundary layer. Actually that hydrodynamic boundary layer come into picture because of the viscosity of the fluid, whereas the thermal boundary layer concept come into picture because there is a temperature difference between the plate and the fluid. If there is a temperature difference between the plate and the fluid, the thermal boundary layer is formed, whereas viscous effect is there. See, if real fluid passes through the surface, then vicinity of the surface, near to the surface, the viscous effect is highly predominant, and because of that hydrodynamic boundary layer come into picture. So about the hydrodynamic boundary layer, right? You studied this part in a detailed manner in the fluid mechanics, right? Hydrodynamic boundary layer. So see, if I'm talking about the plate, if I'm talking about the Prandtl number, now see here, I'm considering a plate. This is the plate, and this plate temperature is Ts, and over the plate that fluid passes, and that fluid velocity is u infinity and the temperature is T infinity. Fine. And I'm assuming that Ts is greater than T infinity. Right. Now see here. In this case, because of the viscous effect, because of the viscosity of the fluid, because this is the real fluid, hydrodynamic boundary layer is formed. So let us assume this is the hydrodynamic boundary layer. Right. And since there is a temperature difference between the fluid and the plate, right, because of this, thermal boundary layer formed. So let us assume this is the thermal boundary layer. So this is the one case where, see, this is the hydrodynamic boundary layer. I am assuming here, this is the hydrodynamic boundary layer, and I am assuming this is the thermal boundary layer. This is the thermal boundary layer, right? So this is the one case where you are observing that hydrodynamic boundary layer is above the thermal boundary layer. Hydrodynamic boundary layer is above the thermal boundary layer. This is the one case. There is another case also where that thermal boundary layer is above the hydrodynamic boundary layer. And there is one case also where the hydrodynamic boundary layer and the thermal boundary layer both are coincide. Is it fine? So, which case is possible? For a particular configuration, right? That is decided by the Prandtl number. Actually, this Prandtl number comments on the hydrodynamic boundary layer and the thermal boundary layer relation. So let us assume if I say Prandtl number is greater than 1 or Prandtl number is less than 1. So what is the relation between the HBl and the TBl? What is the relation between the hydrodynamic boundary layer and the thermal boundary layer? So that relation is shown by or I can say this relation, the relation between the HBl and the TBl we can easily find with the help of the Prandtl number. So this is the significance of the Prandtl number. The Prandtl number tells us HBl is greater than TBl or TBl is greater than HBl, or what is the relation between the HBl and the TBl? This is shown by the Prandtl number. Is it fine? So I hope this significance is clear to you. The Prandtl number tell us which boundary layer, right? If I'm talking about the thermal boundary layer, and if I'm talking about the hydrodynamic boundary layer, so what is the relation between the HBl and the TBl? Which one is the more? Which one is the greater? Which one is the lesser? That is decided by the Prandtl number. Or about this, we can comment on the basis of the Prandtl number. Is it fine? Is it fine? Okay, so this is the significance of the Prandtl number. Now come to the next number, which is Grashof number. Grashof number. Grashof number. So actually this Grashof number is not used in the forced convection. This Grashof number is used in the free convection, right? Grashof number is used in the free convection, and actually this Grashof number is again a dimensionless number, which is the ratio of two forces. One is the inertia force and another one is a buoyant force. Buoyant force. One is the inertia force and another one is a buoyant force. Okay, so what is the inertia force? Inertia force is denoted by Fi. What is the buoyant force? That is a Fb. If you are solving this, what you are getting the Grashof number mathematical expression like this: G beta Lc cube Ts minus T infinitive divided by nu square. This is the mathematical expression of the Grashof number. What is the beta? G is the gravitational acceleration. What is the beta? Beta is the volume expansivity. Beta is the volume expansivity. What is the Lc? Lc is the characteristic length. What is the Ts? Surface temperature. T infinitive is the fluid temperature. And nu is the kinematic viscosity. So this is the mathematical expression of the Grashof number. This is the mathematical expression of the Grashof number. Okay. And there is another number also, that is a relief number. This relief number also used. Relief number. This relief number also used in the free convection. It is ratio of Grashof number and the Prandtl number. If someone asks you what is a relief number, and relief number is denoted by Ra. Reynolds number Re. This is the relief number. Relief number is denoted by Ra. So relief number is a product of Grashof number and the Prandtl number. Is it clear? Is it clear? There is one number also, that is Packlet number. That is Packlet number. Packlet number, and this Packlet number is product of Packlet number. This is product of Reynolds number and the Prandtl number. That Packlet number is a product of Reynolds number and the Prandtl number. Packlet number is product of the Reynolds number and the Prandtl number, whereas the relief number is a product of the Grashof number and the Prandtl number. So this is used in the free convection. Free convection. This is used in free convection. And this is the Reynolds number to Prandtl number. This is used in the forced convection. Forced convection. Is it clear? Is it clear? Now see here. Now see. So these are the some dimensionless number. These are the some dimensionless number. Now see here. If I'm talking about the convection heat transfer. If I'm talking about the convection heat transfer. So please try to understand what are the objectives you are frequently faced. What are the objective? What are the objective in case of the convection heat transfer? Like in case of the conduction heat transfer, there are two objectives. That one is the temperature variation, find the temperature variation, and second one is find the rate of conduction heat transfer. Similarly, in case of the convection heat transfer, there are two objectives. There are two objectives. Most of the problem you are getting these two objectives only, right? These two objectives only. First objective is find the convective heat transfer coefficient. That first objective is find the convective heat transfer coefficient. This is the first objective. The second objective is find the rate of convection heat transfer. The first objective is find the convective heat transfer coefficient, and the second objective is find the rate of convection heat transfer, right? To find this convective heat transfer coefficient, to find this convective heat transfer coefficient, first you find the Nusselt number. First you find the Nusselt number. Right, so before finding the H, first focus on the Nusselt number. Once you know the Nusselt number, then you can easily find the convective heat transfer coefficient. Right, so in case of the convection heat transfer, this Nusselt number is, sometime it is asked that in case of the convection heat transfer, the Nusselt number is function of which dimensionless numbers. Right. So in case of the convection heat transfer, this Nusselt number is function of Reynolds number, Prandtl number, and the Grashof number. In case of the convection heat transfer, the Nusselt number is function of the Reynolds number, Prandtl number, and the Grashof number. Is it fine? Now see here. Convection heat transfer are two types, na? See, convection heat transfer are two types, correct? One is a free convection, another one is a forced convection. Basically three types. Mixed convection is also there, but first focus on the free convection and the forced convection. Free convection and the forced convection. Free convection and the forced convection, right? So in case of the free convection, because in case of the, if I say convection heat transfer, so in case of the convection heat transfer, this Nusselt number is function of Reynolds number, Grashof number, and the Prandtl number, right? But if I say free convection, so in case of the free convection, that Nusselt number is function of Grashof number and the Prandtl number. So whatever the empirical relation you are observing in the free convection, right, whatever the empirical formulas you are observing in the free convection, so there is a Grashof number and there is a Prandtl number, or product of these two, that means there is a relief number. But you are not finding anywhere the Reynolds number. Whereas in case of the forced convection, that Nusselt number is function of Reynolds number and the Prandtl number. Right. So in case of the forced convection, you are not finding anywhere the Grashof number. Right. You are finding the Reynolds number and the Prandtl number, but you are not finding the Grashof number. That is a forced convection. So in case of the forced convection, Nusselt number is a function of Reynolds number and the Prandtl number, whereas in case of the free convection, that Nusselt number is a function of Grashof number and the Prandtl number, right? Now, sometime this question come into mind, ki, sir, how we know that ki which type of convection is predominant for a particular case is there. So which type of convection is predominant? Sir, in this problem, the convection heat transfer, in this problem there is a free convection is predominant or forced convection is predominant, right? So how we can answer such type of question, ki which type of convection is predominant? So to answer such type of question, we find the ratio of Grashof number to Reynolds number ka square. We find the another dimensionless number. This dimensionless number does not have any name, right? There is a Reynolds number, there is a Nusselt number, but this is a dimensionless number, but this dimensionless number does not have any name. But this is very, very important dimensionless number, because this dimensionless number tell us ki which type of convection is predominant, right? So if there are three possibilities, if Grashof number by Reynolds number ka square, if it is that very, very greater as compared to 1, right? In this case, because Grashof number value is high, if Grashof number by Reynolds number square is very, very greater than as compared to 1, so Grashof number is high, Reynolds number is very less. In such cases, free convection is predominant. Free convection is free convection is predominant, or I can say free convection is significant. Free convection is predominant. Predominant, right? Second possibility is if Grashof number by Reynolds number square is very very lesser as compared to 1. In such case, forced convection is predominant. Forced convection is predominant. And third case, if Grashof number by Reynolds number square is approximately equal to 1, then I can say that mixed convection is predominant. Well, both the convection is predominant, that is mixed convection. Mixed convection is predominant. Mixed convection is predominant. Right, so sometimes such type of question is directly asked in the examination. If Grashof number by Reynolds number square is very very greater than 1, then which type of convection is predominant? So you should remember this logic. Okay, now come to the next case, which is relation between the h bar and the hx. So what is a h bar and what is a hx? See here, relation between h bar and the hx, right? What is this h bar? Right, what is the h bar? That h bar is average convective heat transfer coefficient, or simply you can say convective heat transfer coefficient, or average convective heat transfer coefficient. This is denoted by h also. Either you can say h or you can say h bar. What is the hx? This hx is local convective heat transfer coefficient. What is hx? That hx is local convective heat transfer coefficient, right? So question is that what is the relation between the hx and h bar? So let us assume in some problem, let us assume this, if hx is given like this. Let us assume in some problem hx is given like this. Hx is changing with respect to x. If hx is given like this, then in question it is asked find the convective heat transfer coefficient or find the average convective heat transfer coefficient. In question, local convective heat transfer coefficient is given, that variation of hx with x is given. Then in question it is asked find the average convective heat transfer coefficient, right? So you should know the relation between the average convective heat transfer coefficient and the local convective heat transfer coefficient. So to understand this relation, I am considering the, just 1 minute now. Okay, so to understand this relation, I am considering a plate. This is the plate. This is the plate, and perpendicular to the monitor, there is a width which is p. Okay, this is the plate. Okay, and this is x is equal to 0. This is x is equal to L. Actually, x is equal to 0 is known as leading edge. This is leading edge. and x is equal to L, that is trailing edge. This is the trailing edge. This is the trailing edge. At x is equal to 0, that is the leading edge. At x is equal to L, that is trailing edge. Okay, and so this plate temperature I am assuming that is Ts, that length that is L, and I am assuming this length, that means width, which is perpendicular to the monitor, that is B. Ts is the plate surface temperature, and above the plate fluid passes with velocity u infinity and the temperature is T infinity. And as I'm assuming that first assumption is Ts is not a function of x. Right? Ts is not a function of x. That means in the x direction, this is the x direction, this is the x direction. This is the x direction. This is the x direction. So in the x direction, the temperature is not changing with respect to x. Surface temperature, no? Surface temperature is not changing with respect to x. That means surface temperature is constant. That means that first assumption, surface temperature is constant. At any x you will find the same temperature of the plate, same temperature for the plate. Right. So Ts is not a function of x, that is the first thing. And second, Ts is greater than the T infinity. The second important thing is Ts, that surface temperature is greater than the T infinity. So that is second assumption. Okay, now see here. Let us assume at a distance x, let us consider a distance x from the leading edge. This is the distance x, and I am taking a very small element here, a small element here. This is the small element. This is the small element, right? And for this small element, the convective heat transfer coefficient is Hx. At a distance x, the convective heat transfer coefficient is Hx. Area is dA, right? And surface temperature is Ts, because I already assumed that Ts is constant. So from this small element, the rate of convection heat transfer, that is dq dot. The rate of convection heat transfer, that is dq dot. So what is the dq dot? What is the dq dot? So I say this dq dot, this is a small elemental convection heat transfer, that I can say this is the Hx dA, and that is Ts minus T infinity. Ts minus T infinity. I say this is a Ts minus T infinity. So this is a small elemental convection heat transfer. So a small elemental convection heat transfer, that dq dot is equal to, this is the Hx dA, and this is Ts minus T infinity. To find out the total convection heat transfer, I am integrating it. So dq dot is equal to, this is Hx dA, and this is Ts minus T infinity. Right? And what is the dA? What is the dA? That dA is, I say this is B into dx. That dA is B into dx. Okay. So q dot is equal to, what is the limit? Right. Limit, I am assuming, let us assume 0 tends to L. 0 tends to L. So here B 0 tends to L, Hx into dx into Ts minus T infinity. Right. This is the equation number 1. This is the equation number 1. If I am assuming that H bar or H, this is the average convective heat transfer coefficient. Average convective heat transfer coefficient. If I am assuming that H bar or H, that is the average convective heat transfer coefficient, and this H bar is equal to, if I am assuming that H bar is the average convective heat transfer coefficient, and if I consider this average convective heat transfer heat transfer coefficient, and I want to calculate the total rate of convection heat transfer. So by using this average convective heat transfer coefficient, I directly write here that Q dot is equal to, this is H into A, which is a B into L, and that is Ts minus T infinity, right? You can say H or H bar. So this is the equation number 2. This is the equation number 2. So from equation 1 and equation 2, from equation 1 and equation 2, from equation 1 and 2. So from equation 1 and 2, we can say that this H bar B L Ts minus T infinitive, that is equal to B 0 tends to L Hx Ts minus T infinitive Ts minus T infinitive, and that is dx. So this Ts minus T infinitive, Ts minus T infinitive over this B over. So ultimately this H bar is equal to, that is 1 by L 0 tends to L Hx, and that is dx. Okay, this is the H bar. That H bar is equal to 1 by L 0 tends to L Hx dx. So this is the relation between the H bar and the Hx, or if you want to write this mathematical expression in a general way, so you can say this H is equal to this H is equal to 1 by x 0 tends to x Hx dx. So if I want to calculate the average convective heat transfer coefficient, if suppose this is the plate length L, but I want to find out the average convective heat transfer up to this x, then use the this mathematical expression. If you want to calculate the average convective heat transfer coefficient for whole the length L, then find this mathematical expression. So I can say this is the general mathematical expression. So by using this mathematical expression, if Hx is given, then definitely you can easily calculate the average convective heat transfer coefficient. Is it okay? Okay. Now come to the next concept, that is energy balance. That very important concept. Energy balance. Energy balance concept. Energy balance concept. So to understand the energy balance concept, again I am considering a plate here. Right. This is a plate. Okay, so again, this is the x is equal to 0. This is x is equal to L. That complete length of this plate is L. That width, that is B. That is B. Width is B. Width is B. Width is B. Okay. So if you draw the coordinate system, so this is the x direction along the plate, x direction, and perpendicular to the plate, y direction. Y direction. Right. So if I want to apply the energy balance at y is equal to 0, at y is equal to 0, where I am applying the energy balance at y is equal to 0, at y is equal to 0. So at y is equal to 0, can I say, at y is equal to 0, can I say the rate of conduction heat transfer to the fluid is equal to rate of convection heat transfer? Can I say? Yes, sir, we can say. At y is equal to 0, at y is equal to 0, at y is equal to 0, rate of conduction heat transfer to the fluid, rate of conduction heat transfer to the fluid is equal to rate of convection heat transfer at y is equal to 0. At y is equal to 0, the rate of conduction heat transfer to the fluid. So what is the rate of conduction heat transfer to the fluid? So this is the kf, right? This is the kf, or first na, right? Okay, fine. The kf into area. So area from where the conduction occurs. So that is B into L, right? Or simply I say this is A into dt by dy at y is equal to 0. And this is equal to the rate of convection heat transfer. And what is the area from where the convection occurs? That is a A only. So HA, and this is Ts minus T infinitive. And I'm assuming here Ts is greater than T infinitive, and this Ts is not a function of x, that means Ts is constant. Okay, so this A you can easily eliminate, right? So ultimately what you are getting this minus kf into dt by dy at y is equal to 0 is equal to that is h Ts minus T infinitive, right? Now see here, calculate both side by LC. So this is the one energy balance. First focus on this. Na? This is the energy balance. From directly you can expect the question. Because already number of times that question came from here only, right? Now both side multiplied by LC. So this is kf dt by dy at y is equal to 0 into LC is equal to, this is h into Ts minus T infinitive into LC. So that HLC by Kf is equal to, this is minus dt by dy at y is equal to 0 into HLC by dt by dy at y is equal to 0 into LC divided by, this is Ts minus T infinitive. And this HLC by Kf, this is nothing but the null set number. So you can say this is the mathematical expression of the Nusselt number also. Okay, this is the Nusselt number. Okay, so see, there is a concept of convective heat transfer coefficient and the local convective heat transfer coefficient, and similarly there is a concept of local Nusselt number and the Nusselt number also. So if I want to the local Nusselt number, so I write here hx into x, and this is the kf is equal to, this is minus dt by dy at y is equal to 0 into x divided by, that is Ts minus T infinitive. Right, so this is the local Nusselt number. This is the NUX. This is the local Nusselt number, and this is the average Nusselt number. This is the average Nusselt number. Is it fine? Is it clear? Okay. If it is clear, then come to the next important part. In external force convection. In the external force convection, I already told you, there is a formation of the thermal boundary layer, as well as there is a formation of the hydrodynamic boundary layer, right? There is a formation of thermal boundary layer and there is formation of the hydrodynamic boundary layer. So what is the relation between the thermal boundary layer and hydrodynamic boundary layer, right? So to understand this, see here. If I say external convection is there, or external force convection is there. If I say external force convection is there, then might be possibility the flow may be laminar or turbulent now. The flow may be laminar or turbulent now. Yes, sir. The flow may be laminar or turbulent. The flow may be laminar or turbulent. And how you can identify the flow is laminar or turbulent? On the basis of the Reynolds number, or I already told you. So if there is external flow, so in case of the external force, or I can say if there is an external flow, first find out the Reynolds number, and Reynolds number is, this is a rho u infinitive x by, that is mu, or you can say u infinitive x by nu. First find out the Reynolds number, or I can say local Reynolds number, because in case of the external flow, this Reynolds number is changing with respect to x. What is the x? Distance from the leading edge, na? Distance from the leading edge. So as we move away from the leading edge, right? So if x increases, the Reynolds number increases. So see, as x increases, then definitely the Reynolds number changes, right? And if the Reynolds number changes, so Reynolds number is dependent on the space, or Reynolds number is dependent on the x. That's why we are using the local Reynolds number. So whenever some parameter is changing with respect to x, then we are using a term which is local. So what is the REX? What is REX? That REX is the local Reynolds number. Right? What is the REX? That REX is local Reynolds number. So if you are calculating the local Reynolds number, at a particular x, if it is less than or equal to 5 into 10 to the power 5, then flow is laminar. And if the REX is greater than 5 into 10 to the power 5, then flow is turbulent flow. Then flow is turbulent flow. So what is the relation between the hydrodynamic boundary layer thickness and the turbulent boundary layer thickness for laminar flow? If flow is laminar, if flow is turbulent. So if flow is laminar, then this delta Hx to delta Tx is equal to Prandtl number to the power 1 by 3. And if flow is turbulent, then delta Hx is approximately equal to delta Tx. What is the delta Hx? This delta Hx is local hydrodynamic boundary layer thickness. And what is the delta Tx? This is local thermal boundary layer thickness. Is it clear? And how you are calculating the delta Hx? See, once you know the delta Hx, then you are easily calculate the delta Tx. Then how you are calculating the delta Hx? So to calculate the delta Hx, we should know the Blasius result. That concept came from the fluid mechanics, Blasius result. So from the Blasius result, I am talking about the Blasius result now. Blasius result. I am talking about the Blasius result. So if the flow is laminar, then how the boundary layer thickness, or how we calculate the boundary layer thickness? And if flow is turbulent, then how we calculate the boundary layer thickness? So if flow is laminar, then delta Hx is calculated by using this mathematical expression 5x root over Rex. Right, 5x root over Rex. And if flow is turbulent, then delta Hx is calculated by using this mathematical expression 0.376x Rex to the power 1 by 5. 1 by 5. Right. So if flow is laminar, then calculate the delta Hx by using this mathematical expression. If flow is turbulent, then use the hydrodynamic boundary layer thickness by using this mathematical expression. Is it fine? Is it fine? Right. Now see here. In case of the turbulent, there is no problem, because in case of the turbulent flow, the delta Hx is almost equal to delta Tx at any x. Right. Delta Hx, that thickness of the hydrodynamic boundary layer thickness and the thickness of the thermal boundary layer thickness is almost same in case of the turbulent. But in case of the laminar, there are three possibilities. In case of the laminar flow, or in case of the laminar boundary layer, right, the first possibility is if Prandtl number is greater than 1. If Prandtl number is greater than 1. So if Prandtl number is greater than 1, that means nu is greater than alpha na. Nu is greater than alpha na. Prandtl number is greater than 1, that means nu is greater than alpha. If nu is greater than alpha, then I can say at any x that delta Hx is greater than the delta Tx. Delta Hx is greater than the delta Tx. If let us assume this is a plate. If this is a plate, this is the thermal boundary layer. This is the thermal boundary layer. This is the thermal boundary layer. This is the hydrodynamic boundary layer. This is the hydrodynamic boundary layer. So this is the hydrodynamic boundary layer, and this is the thermal boundary layer. So at any x, delta Hx is greater than the delta Tx in case of the laminar. So this is the first case, and such type of case you observe in the heavy oils. Heavy oils, that means heavy oils means oils. Heavy oils means oils having a higher viscosity. Oils having higher viscosity. Right. So this is the case number 1. This is the case number 1. Now come to the case number 2. Come to the case number 2. Case number 2, where Prandtl number is less than 1. If Prandtl number is less than 1, that means nu is less than alpha, or alpha is greater than nu, right? And in this case, delta Tx is greater than the delta Hx, right? So for this case, if this is the plate, this is the thermal boundary layer, and this is the hydrodynamic boundary layer. This is the hydrodynamic boundary layer, and this is the thermal boundary layer. This is the thermal boundary layer. So example is liquid. Liquid metal. Example is liquid metal. If metal is in liquid condition, then such type of condition is there. Right. Next, third. Prandtl number is approximately equal to 1. Prandtl number is approximately equal to 1. So nu is approximately equal to alpha. At any x, delta Hx is approximately equal to delta Tx. Okay. See here. In this case, at any x, if this is the thermal boundary layer, then this is the almost coincide, na? Sorry. Okay. So thermal boundary layer, this is the hydrodynamic boundary layer, and thermal boundary layer, right? Both coincides. Example, gases. Example, in case of gases, you might observe such cases. Is it clear? Is it fine? Okay. Now come to the next part, that empirical relation. In case of the external force convection, forced convection. In case of external forced convection, you are observing two cases. You are observing two cases. That first one is constant wall temperature case. First one is a constant wall temperature case where Ts is not function of x. That means Ts is constant. Ts is constant, right? And the second case is constant heat flux case. Constant heat flux, constant heat flux case where q dot is not a function of x, q dot is constant. Q dot is constant, right? Q dot is constant. So constant wall temperature case, that means see here, constant wall temperature case means if there is a wall, if I am assuming there is a wall, if there is a wall like this, or there is a surface like this, sorry, if there is a surface, the surface is like this. So if the surface is like this, na, on this side, phase change occurs. So if let us assume there is a steam and that steam is converted into liquid. So we know that if phase change is there, then during the phase change the temperature is constant. So if there is a wall and in this side phase change is there, so here the temperature is, let us assume one atmospheric pressure, steam is converted into water, so that saturation temperature is 100 degrees Celsius. So here the temperature is 100 degrees Celsius, 100 degrees Celsius, 100 degrees Celsius, like this. Is it clear? So this is the constant temperature case. This is the constant temperature case. Okay, and what is the constant heat flux case? Constant heat flux case, if there is a wall, if wall is like this, and if wall is like this, and there is a heating coil, that heating coil is wrapped in this wall. Then in this case the q dot is not a function of x. This is the heating coil. Then this is a case of the constant heat flux. Okay, and this is a case of now constant wall temperature. So for the constant wall temperature, there is a wall. So this is the wall, and in this side phase change occurs. In this side phase change occurs. Here the phase is, let us assume that is a gaseous phase, vapor phase, and this side that phase is liquid, and vice versa, right? So if phase change is there, wall temperature is maintained constant. If heating coil is wrapped like this, then wall is at the constant heat flux condition. Okay, so first discuss about the constant wall temperature case. So constant wall temperature case. If constant wall temperature case is there, so again there are two possibilities. That first possibility is flow is laminar, and the second possibility is flow is turbulent. If flow is laminar, then empirical relation NUX is equal to HX by KF is equal to, this is 0.332 REX to the power 0.5 and Prandtl number to the power 0.33 applicable. This is the empirical relation. And if flow is turbulent, then NUX is equal to 0.029 REX to the power 0.8 and Prandtl number to the power 0.33. Prandtl number to the power 0.33. So in case of the laminar flow, this mathematical expression is applicable, and in case of the turbulent flow, this mathematical expression is applicable. Right. So sometime in question it is asked how the that convective heat transfer coefficient, how the convective heat transfer coefficient depends on the x. So you can easily formulate from here, right? Because see here, Hx is now here x in the Reynolds number mathematical expression. If you open the Reynolds number, rho u infinitive x by mu, right? So ultimately you are getting x to the power, this is 1 by 2. Now this x is in denominator, right? So this is minus 1. This is minus 1. So ultimately I can say this is Hx is directly proportional to x to the power minus 1 by 2. X to the power minus 1 by 2. So in the x direction, the convective heat transfer coefficient decreases. How it decreases? See, Hx is directly proportional to x to the power minus 1 by 2, or you can say Hx is directly proportional to 1 upon x to the power 1 by 2. And in case of the turbulent flow, that Hx is directly proportional to same x 0.8. This nux you can write Hx into x by kf. Okay, so x 0.8. So I think this comes minus 1 by 5, because this is 4 by 8, 4 by 5, 0.8, that means 4 by 5. Now 4 by 5 minus 1, so it is minus 1 by 5. Okay, so in case of the turbulent, this relation is applicable, and in case of the laminar, this relation is applicable. Okay, in both laminar as well as turbulent, that convective heat transfer coefficient decreases as x increases. Okay, and this is also true. Hx for turbulent is greater as compared to Hx for laminar. Hx for turbulent, the convective heat transfer coefficient in case of the turbulent flow is always higher as compared to the convective heat transfer coefficient in the laminar. Is it clear? Okay, now come to the second part. Again, in this side laminar and in this side turbulent. Okay, now in case of the laminar, if you are calculating the average convective heat transfer coefficient, how you are calculating this? Remember that h bar is equal to 1 by x, 0 tends to hx, 0 tends to x, hx dx, by using that mathematical expression. So if you are calculating the relation between the h bar and the hx, so h bar is equal to, this is 2 times of hx in case of the laminar. Whereas in case of the turbulent, that h bar is equal to 5 by 4 times of hx. 5 by 4 times of the hx. Is it clear? So this is the case of the constant wall temperature. If constant wall temperature is there, then this mathematical expression are applicable. Okay, and if there is a constant heat flux case, if there is a constant heat flux, right? If there is a constant heat flux case, so in case of the constant heat flux, again two possibilities, either flow is laminar or flow is turbulent. Flow is laminar or flow is turbulent. So if flow is laminar, so see, dependency will not change. So what change? That only this factor, na? This factor. Here it is 0.332. Now see here. In case of the, just 1 minute. Okay. In case of the laminar, this local Nusselt number is equal to, this is 0.453 Rex to the power 0.5 Prandtl number to the power 0.3. Whereas in case of the turbulent flow, this nux is equal to 0.0308 Rex to the power 0.8 Prandtl number to the power 0.33. Is it clear? So that dependency, here that dependency of hx on x is same, right? The only changes that occurs in this factor, in case of the constant wall temperature, this factor is 0.336, 0.336 na? Just 1 minute, sorry, 0.332, 0.33, just 1 minute, I will check once. That is 0.332, yes, 0.332, and here 0.0, ठीक, okay. And in case of the turbulent flow, here the factor is 0.0209, here the factor is 0.0308. So definitely, if you are calculating the convective heat transfer coefficient in the constant heat flux case, you are getting more value as compared to the constant wall temperature. Why? See here, this factor is more na, in both the cases. In both the cases, in case of the laminar, this factor is 0.453. In case of the constant wall temperature, that is 0.332. In case of the turbulent, this factor is 0.0308. In case of the constant wall temperature case, turbulent, 0.0209. So definitely, Hx, if you are calculating the Hx by constant heat flux case, that is always greater as compared to the Hx value in case of the constant surface temperature or constant wall temperature. Similarly, you can comment on the Nusselt number also, NUX, constant heat flux case, more, NUX constant wall temperature. Is it clear? And at what, see, if I want to find out the percentage increases, if I am comparing the constant heat flux and the constant wall temperature case, and if I want to find out the percentage increase in constant heat flux case as compared to the constant wall temperature case, right? Percentage increase. So percentage increase in case of the laminar. So what is the percentage increase? So that is see here, that factor 0.453 minus 0.332 into 0.332 into that is 100%. So this comes approximately 40%. So I can say, see, if you are calculating the convective heat transfer coefficient, if you are calculating the convective heat transfer coefficient in the constant heat flux case, let us, laminar condition is there. If you are calculating the convective heat transfer coefficient in constant heat flux case, right? And if you are calculating the convective heat transfer coefficient in the constant wall temperature case. So constant heat flux case, the convective heat transfer coefficient is approximately 40% more as compared to the constant wall temperature case. Is it clear? And similarly, you can comment on the Nusselt number also, same 40% increases. Similarly, you can comment on the heat transfer also, convection heat transfer also. The convection heat transfer in case of the constant heat flux case is around 40% more as compared to the constant wall temperature case. If flow is laminar, right? And similarly, in case of the turbulent, that is 0.0308 minus 0.0209 upon 0.0209 into 100%. So this comes around 6%. This comes around 6%. Is it clear? So I hope you can understand the logic, you can understand the concept of the external force convection. I hope you can understand this. Is it clear? So this is all about the external force convection. So I hope you can understand all the logic, all the concept. So thank you so much for this lovely session. Thank you so much. Bye bye. Take care and have a good day.